Hello students, today we will discuss about the application of UJT as a relaxation oscillator. So for that purpose, let us see the biasing circuit of the UJT that can be used as a relaxation oscillator. Now there are two resistors R2 and R1 which are externally connected to this voltage source class VBB. There is another resistor R which is connected to the emitter and a capacitor between the emitter and the base 1. Now to see how this UJT works as a relaxation oscillator, first of all we will see the voltage across C, which will be a sawtooth wave like this. So let us first explain how we can get a sawtooth wave from the UJT when we take the voltage across C. For that purpose, let us take the time t to be 0. So let us consider at t equal to 0, the voltage across the C, which is Vc, is equal to 0. But it is not actually 0 because, as we know, that the emitter base 1 junction will be acting as a diode. So the cut-in voltage will appear here and that will be around 0.7 volt. But for the time being, we are ignoring that cut-in voltage and we assume that at t equal to 0, the voltage across the C is 0. That means this capacitor is fully discharged. C is in fully discharged condition. So C is in fully discharged condition. So let us start from this situation. So when this capacitor is fully discharged, the voltage here is 0, which makes this emitter base 1 reverse biased. So as it is reverse biased, no current will flow, no IE will flow through it. So as no current is flowing through the emitter and base region, the capacitor will now start charging through this resistor R. So it will start charging through resistor R. Now the voltage across C will start increasing. As the voltage across C, that means if the Vc value is equal to a voltage called peak voltage, which I am denoting as Vp, equal to Vd plus eta Vb. So this is the voltage that is required to make this emitter and base junction forward bias, which already we have discussed in our earlier videos. So capacitor is charging. Once the voltage across the capacitor reaches Vp, which will make this emitter and base junction forward biased, and current IE will start flow. Current I will now start flow. Current IE will start flowing through. So as this current IE flows through this EB1, this capacitor now will discharge through R1 and it will discharge very fast as this value of R is taken a very low value around 100 ohm or even less than that. So if the value of the R1 is very small, then the capacitor will discharge very fast, which is denoted by this graph. So this is the discharging of the capacitor. So capacitor is charging from 0 to Vp. Once it reaches Vp, so it will start discharging through the UJT, and the discharge time is very small. So if I see the charging time, that will be nothing but time constant RC, and for discharging the time constant will be R1C. So when this C is fully discharged through this R1, again the voltage across C will become 0, and again this portion will become reverse biased. So once it is reverse biased, no current will flow through it. Then at that moment the C will again charging through this R up to Vp. So C will again now charge up to Vp. Once it reaches Vp, will again start discharging through R1, and this whole process will repeat with time. This kind of wave is called sawtooth wave. Sawtooth wave. So we can generate a sawtooth wave using a relaxation oscillator when we take the voltage across the C. On the other hand, if you see the voltage across R1, which is denoting by VB1, then you can see that wherever the capacitor is charging, this portion is reverse bias, that means it is in the cutoff region. So as it is cut off, so the voltage drop across this R1 will be equal to 0, which is denoted by this one. So the voltage across R1 will be 0 until the capacitor charges up to Vp. So once the capacitor charges up to Vp, this diode will fire. Once this diode will fire, a huge amount of current will flow through it. So suddenly the voltage across R1 will rise. Now this capacitor will slowly discharge through it, and accordingly the voltage across R will also decay or decrease exponentially. So the voltage across R1 will decay exponentially as the voltage across C is decayed. Same thing again, if the voltage across C, that means Vc becomes 0, it will become cut off. Once it is cut off, the voltage across R1 will be equal to 0. So these whole things will repeat. So this is the voltage pattern that we are getting across R1. Now here you can see, unlike this sawtooth wave, what you can notice here is that the output voltage is 0 from here to here. That means I can say that the UJT is in relaxed condition. After that, now it starts doing its work. UJT start doing its work. It's going up, again it is going down. So again it is in relaxed here, giving from here to here. So as the oscillator is relaxed after a certain interval of time, we call it as a relaxation oscillator. So this kind of two waves we are getting from the UJT. I can get a sawtooth wave, I can get a wave pattern like this. I can also take the voltage at this point also. This will be V2. So it will be just opposite of VB1. That means whenever this is in the cutoff, I will get the maximum voltage here. That means whenever the capacitor is charging, the VB will be maximum, and after that it will decay slowly. So if you see from the practical point of view, if I want to see the values of this R2, R1 and R, let us consider the UJT 2N2646 is a very commonly used UJT. If we use 2N2646 and if we want to implement the sawtooth wave using this UJT, then we have to take the values in this way. R we can take 10 kilo ohm, or we can take more than 10 kilo ohm. R2 will be equal to 1 kilo ohm. R1 we can take 100 ohm or even less. C we can take as 1 microfarad or less than 1 microfarad. So if I take these values, then I can see that the time constant during the charging time, which is RC, so that will be equal to 10 kilo ohm multiplied with 1 microfarad, which gives me 10 millisecond. On the other hand, if you multiply R1 and C, which is the time constant during the discharge time, so that will be equal to 100 into 1 microfarad, so that will be 10 to the power minus 4 second. That means 0.1 millisecond. So you can nicely see that the time required for charging will be more compared to the discharge. Discharging time is very small, it is 10 to the minus 4, and charging time is 10 to the power 10 millisecond, which is quite high compared to this one. This is how we can implement the sawtooth wave using an 2N2646. For that purpose, you have to take this R1 very small compared to this R and R